Well, thank you for attending to this presentation. I'm Albert Pujol, and me and Juan Luis Cano, are going to talk about Satellogic and how we use Python in Satellogic to understand the world. First, I'm going to talk about just a bit about Satellogic, what we do and who we are. Also, just a bit also on where we use Python in our satellites and outside our satellites. And I'm going to focus on what we do here in Barcelona. That is the data science related to the use of satellite images in imaging, and it's used for generating value for our clients. I'm going to talk about what kind of data we work with, what kind of problems we solve, and what kind of infrastructure, both hardware and software, we use to solve those problems. And at that point, I will be like deciding to see some Python code, and then it's going to come Juan Lu and show you something in Python or like code. So what is Satellogic? Satellogic is a company that designs satellites, that constructs satellites, that sends satellites to the space, and that use those satellites to generate value for our clients. The satellites that we make are what is called Earth observation satellites. So are satellites that have cameras in it. We have two kind of cameras in the satellites. One that is like what is called multispectral camera, hyper-resolution multispectral camera. It means that it's a camera that allows us to get pictures of the Earth at 1 meter resolution per pixel, and with 4 bands, red, green, blue, and near infrared. And we have in each satellite another camera that allows to get images of what is called hyperspectral sensors. And these sensors are a kind of sensor that give us much less resolution in terms of spatial resolution, but much more detail in terms of electromagnetic spectrum. So instead of getting like 4 bands, we're able to put the electromagnetic visual spectrum in 40 bands. This allows us to have a very a capacity of distinguishing between colors that our A is not able to see. And somehow we can see the green of a leaf that is from a healthy plant and distinguish it from the green of a plant that has some disease and that our A is not able to see. We have right now 8 satellites giving turns around the planet. These satellites are like flying at a speed of 26,000 kilometers per hour, something like that, and are flying at 400 kilometers of altitude. We plan to send and to have to send this year like 8 new satellites. And our roadmap is to have a constellation of 200 satellites covering all the planet. This will allow us to get a picture of the whole Earth, 1 per day. Satellogic is a lot of people. It's more than 160 people, distributed mainly in Buenos Aires in Argentina, where we have the headquarters with the team that designs the satellites and that controls the satellites. The satellites after that are assembled in a plant in Uruguay, Montevideo. And when we have the satellites ready, we pay rockets from China, India, Russia, whatever, to send them to the space. With those satellites in orbit, we have part of the company that have developed the infrastructure to store all this data and to deliver this data, this huge amount of data that is mainly in Tel Aviv. And here in Barcelona, we have all the team that gets those images, all that data, and use artificial intelligence to understand what there is in the images to get value for our clients. So we provide to our clients images, and we provide insight from those images. And we have also part of the team in China, mainly business developers. So as a tail Satellogic is a company that uses Python almost in all the processes, both processes inside the satellite and outside the satellite. Just to illustrate with processes we solve using Python, imagine that a client asks us for knowing which is the production of cotton of a country. When someone asks something like that, because he wants, as an example, to know which is going to be the price of cotton to buy or to sell or whatever, first of all, what we do is, what we have to do is to schedule in our satellites the acquisitions of the images of the country, of that country. So this implies a lot of algorithms to predict the positions of the orbits of all the satellites that we have. This is done in Once we have all the orbits of all the satellites, we can know which satellite is going to pass over the target and when it's going to pass. So we can tell to that satellite at that moment on time you have to take a picture. To do that, also using Python, we send this task to a ground station. This ground station is an antenna that is close to Icelandia, something like that, and sends that information to the satellite when the satellite passes through or close to the antenna. So sends the information to the satellite when at that time you have to get a picture pointing to this orientation. All these processes, most of them are developed in Python. To do it correctly, the satellite has to know where he is and where he is pointing at. So for doing that, there is a lot of technological stuff in it, but we have to we use among other things star trackers to use the position of the stars, read it with cameras to triangulate and to know where the satellite is looking for. After knowing where we are, we have to send information to our actuators in the satellite to move it, to change the attitude, and to point to the target. Again, all these things happen in Python. We acquire the image, we have to pack the image, like as we would do it here, to store it in the satellite. And when we pass through a ground station, close to a ground station, we have to point to the ground station and send that image to the ground station so it can be sent to our data warehouse infrastructure. Again, all of them developed in Python to storage an amount of data that is planetary amount of data. So it's a huge amount of data, and to be able to deliver that information to our clients. So we have also a delivery platform developed using Python. Until now, we only have images, and what we do here in Barcelona is to use machine learning, artificial intelligence, and data science algorithms to understand what's on those images, to detect where are the fields of cotton, and to measure which is the production of cotton of the country. This is the kind of things that we do, and all the part of the machine learning, artificial intelligence, all of them is done in Python here. I'm gonna focus more now in exactly what we do here in the data science solutions team of Satellogic, and I'm gonna illustrate it showing typical problems we solve for our clients. This is a typical problem, or different typical computer vision problems that we solve. This is a typical problem of counting trees. We have some clients that have huge amount of trees and want to know which is the surface that has been harvested of their trees. If there are trees that have grown in places that shouldn't grow because the trees have to have separation between them. To do that, here we only have now 8 satellites, from which only 3 are functional. So we use our imagery, and we use imagery from other sources of the data. So other satellites, both public and private. Other kind of computer vision or machine learning problems that we solve is regression problems. This is sometimes our client have some sources of data that are cheap data and wants to get transform them in sources of data that are much more expensive. As an example, you can fly a drone over a surface or get or imagery with red, green, and blue, and something that we make is try to estimate what would be the response of a thermal sensor that is much expensive and is difficult to get using this high resolution color image information and some bands of other satellites that are close to infrared. So we transform from one kind of information to another, and to get like from low resolution to high resolution, this kind of thing. Another kind of problem that we solve here is to predict how the things are going to be in time. So we have, as an example, a machine that makes the harvest in some crops that have the client, and these machines measure exactly which is the yield produced in each point of the field. So we have this at the end of the season. With that information and with an historic of images of all the process, what we do for our clients is to predict in each point of time which is going to be the end production of yield. So we can detect in time and in place if there are some places that are going to have problems on production. And we can tell to our client, you have to take care in this place because we have detected that you are going to lose your production there. Other kind of problems that we do is what we call image segmentation. That is, for each pixel of the image, tell me which is the kind of use that the people is doing of the land. So we get images, and we have to classify each pixel in if it's a forest, if it's a agricultural land, if it's an urban area, if it's an industrial block. And why the countries want that information? They want this information because taxes in some countries are depending on the use of the land that you're doing. So, and there's a lot of countries that they don't have that information like on time. And also another another thing that our clients use to ask for is, with this I can measure which is the amount of forestry that you have, and this is an asset that you have to protect as a country. With this, we can detect the changes in this asset. So we can tell you, you are losing your forest here at this moment, so you can act. Another kind of thing that we do is to detect changes, like relevant changes to protect your assets, your huge infrastructures. So we can monitor infrastructure. In this case, it's a huge pipeline, thousands of kilometers of pipeline that has to be monitored. And images change a lot between days. This is like one day image, 2 places, another day image, in the same place. And the image from one day to the other change all around. Things grow, but you are interested not in that this thing was green here and here. You are interested in that the river had changed, or that someone had constructed something, or that someone can have some machinery that can break your pipeline. These kind of things. So we have to make algorithms, or we make algorithms that learn to detect changes, that learn to detect relevant changes, and learn to explain those changes, so that our clients can use that information. What we use for solving all these things? What kind of data do we use for solving all these problems? As I said before, we use Satellogic data, is the imagery that we get from our satellites, but we use whatever other source of data that help us to solve the problem. So we use third-party satellite providers. For elevation models, we use a lot of layers of information. As an example, elevation models are public information that give us, tell you the altitude of each point of the Earth. If you suppose that you are looking for pineapples, you don't expect to find pineapples at 3,000 kilometers altitude, or you don't expect to find it in very places with a lot of slope or in shadow. So we can use all this information to add it to our layers of imagery to make much better models to predict where things are or what we are seeing. How is our data? First of all, it's huge. Our algorithms work with a lot of data, very heavy data. A typical project may supposed to work with 20 gigabytes of data a day for processing, and we expect to get 7 terabytes of data per day at 2021, more or less. So it's a lot of data. Besides that, our data, to try to understand what there is in the image, have a set of challenge or several challenges due to how the image change, or the changes that are not related to the content of the image. When one see like the Google Earth imagery, the people expect to have very clean images, and this is not true. This is very far away from reality. 70% of the world is covered by clouds. So it means that when you get a picture, you get a cloud for sure. So something is being occluded, or is changing the contrast of your image, or is changing the content of the data that you are going to use to predict things. So it's a very challenging problem. You have changes, no matter that you are getting a satellite that is 400 kilometers away from the target, you get images like tilted from different perspectives of the objects. And for very high objects, it makes difference in perspective. And you have also difference in shadows, obviously, depending on the overall array that you get the things. So you have a lot of variations. Another important thing on our data sets, I don't know how many of you work in data science, but we have very unbalanced data sets. It means if we pick randomly windows of data, and we will, in this example, suppose that we want to distinguish between trees and houses. If we would get at random samples to train our algorithms, we will get almost all the time trees, and maybe, if we are lucky, 1 or 2 images of houses. So it's very unbalanced data sets, and this is bad for our algorithms. So we have to make strategies to compensate for all this. Another characteristic of our data is that we have plenty of different formats of data to start working with. So we have different projections of data, of maps. We have different format files, like shape files, different whatever. We have different images that have to be combined in mosaics. So we have a lot of stuff to do with that. For all these, we have developed here our own platform to handle all these things. Our platform is developed in Python, obviously. We love Python. And it's a platform that is designed to trace all the process of data science development, to reduce the code that our data scientists do, to reduce the data sets that they do, to reduce the models that they use, to simplify the life of the data scientists, to put their work into production, and to put it in a distributed way. We have developed our own engines for doing that, and we work with Azure, with Microsoft, is the life. Using blob storage, PostGIS databases. Obviously, we use Dockers, and we use RabbitMQ, CosmoDB for internal processes mainly. And for the processing thing of the GIS information, we work with Telluric. Juan is one of the fathers of Telluric, that mainly use Rasterio, J.L, et al. And our data scientists do whatever they want. They work in Python, they make their scripts in whoever they want, and directly they put it inside of platform or core platform, and the platform distributes it and make all the work. So they usually work with OpenCV, with scikit-learn, with PyTorch for deep learning, Keras, and TensorFlow, and these kind of things. And now, Juan will.
Thank you very much, Albert. Okay, so we don't have much time left, so I will go very quickly, like try to compress what's happening between these beautiful images that you already saw and what's in reality, because this is very similar to many back-end and front-end divisions that you might see out there in the wild. So far Albert explained more or less this thing, and I'm going to compress in 5 minutes what happens behind the curtain, so to speak. So basically what happens on Earth when one client is asking, okay, so I want to capture for several cities of Barcelona, or maybe I want to cover this area here or something like that. And we made a web application that we call Blackwing internally. There's lots of geeky references everywhere, of course. And when they put here these points that they want to capture, or the areas or whatever, then there's a process. Then there's a, well, all of this is a Django application, and then there are some celery tasks that try to compute, of course, like what are the passes that the satellites are going to go over this area, so we can say, okay, so I have these opportunities and the cloud coverage is this average, so my success rate is going to be more or less this size, and so on and so forth. Then when we have that list of opportunities, then we have to mix that with all the other projects, because of course there's one client that wants to capture some desert in Argentina, for example. But if there's another client that wants to capture an area that it's very close, then there might be competing opportunities between the satellites, and we need some optimization process to try to conceal all those opportunities and try to reach some agreement, so to speak. So again, there is another application that we call Satellops, that in combination with other things, it says, okay, so now that I have all these opportunities and that I try to maximize some metric, for example, the square kilometers that I'm going to capture, or the money that I'm going to earn, or some other metric that I can define, then we make what we call the plan. And the plan for the satellites is just a very simple sequence of instructions that is something like, okay, so at 18:05:32 UTC, turn on the camera, then 5 minutes later, start some maneuver to point to some specific point on Earth, and so forth. So on board, there's no knowledge of what's going on in the satellite, and we try to do all that planning on the ground because our resources in space are limited, as we will see next. So again, we use, each of these services is a separate Django application. We do lots of processing with Celery and etc. And then we also use some other libraries like GNU Radio, for example, if some of you know like software-defined radio. And of course, there's lots of magic involved because at some point, all this information goes in orbit to the satellites, and I don't have a clue how that works. So this is what happens in orbit. This is an internal joke because you can see, if you look for Milanesa, which is the name of one of our satellites, that it's always like very funny Argentinian jokes. So when I was doing the interview for Satellogic, I said, okay guys, I'm a Python fanatic and free software and blah, blah, blah. But how involved are you, or how involved are you with Python really? And apparently it turns out that there's Linux running in orbit in our satellites, and that these Linux machines run Python actually. So to give some more detail about what we're doing, we have like 6 Linux computers on board with varying degrees of computing power and architectures and etc. I cannot give much details about them, but basically they go between like your grandma's smartphone and your dad's laptop, more or less. Like that's the range of computer power that we have in orbit. So it's not super, like we cannot do Bitcoin mining in space, not especially. And all these computers, they run Debian Yesi, so like not the present stable version, but the previous one. So we're using Python 3.4.2. That's important. Well, that's a great thing because we're not using Python 2. That's great already. By the way, remember Python 2, end of life next year. I do consulting. No, I'm joking. So we manage all the... and that's it. I'll try to go quicker, no problem. And we can use nice stuff like async I/O, for example, because for some of the projects we do lots of asynchronous processing. And we can afford uploading some dependencies. For example, we use a library that is called Atters, that allows you to create like Python classes like in an easier way for some use cases, and some other stuff. Of course, we don't upload like lots of stuff to the satellite because it's super expensive, but some things we can afford. But then the cons is that in Python 3.4, async I/O was in its infancy, and actually there were some breaking changes between Python 3.4.2 and 3.4.3. So, and it's not that easy to find the 3.4.2 documentation online, and we have to read some old async I/O tutorials. You know, all these tutorials that come before the point when it was actually nice to use. So, and we don't have the async await keywords, so like doing async code is not that nice. And last Monday, this week, they said that they released Python 3.4.10, and it's officially end of life. So now they have like no support whatsoever, and most of the dependencies are already dropping it, so we have like to pin everything to quite old versions. So we can benefit from the Razor's Edge. And then this is a piece of code from our executor, and as I said, it's super simple. We have like some list of instructions, and we sort it by execution time, or the beginning of the execution time, and then we say, okay, if this instruction still has to be executed, so like its time hasn't passed already, then I'm going to schedule it, and if not, I'm going to discard it and log something. It turns out we discovered while developing this project that we cannot, with async I/O, schedule like all the instructions, because one approach would be, okay, so you have the list of instructions, put everything into async I/O, and then wait for the thing to complete. It's not that simple, because apparently there are some performance issues, so we have to go like one by one and be careful not to schedule too many things. And the downside of that is that we have to add some margin to the instructions, because things are not instant, and for example, there is like some 100 milliseconds delay for some operations in async I/O, so like with our computer power. So this can lead us to lose some operations. So we cannot afford that normally. And then in general, how do we do stuff on the satellite? Well, we do lots of different things in the satellite. There are some nodes in the network that communicate over SSH. For some other nodes, we use a protocol that is called CoAP, Constraint Application Protocol, that is like a lightweight version of HTTP. So we try to use that to like command operations between the nodes of the network. Launching a sub-process in a machine, whatever. So there are lots of different ways in which you can do stuff with satellites. So what we try to do is that we have some common API that is all async I/O coroutines. So what they do is, okay, so if this operation that I want to take, like take a capture, for example, take a picture, if that's a blocking operation, then I'm going to run it in a thread executor. And if not, if it's already a coroutine, something I can run asynchronously, then I'm going to use that and leverage that so I don't block the rest of the application. So, just as some final remarks, on the ground we're migrating everything to Python 3.7, yay, F strings, and embrace the future. Not all of our projects are in Python 3.7 yet, but I think we can afford to have it by the end of the year or even earlier. And in general, we face lots of challenges everywhere. For the geospatial processing, we're all the time working upstream with other libraries such as Raster.io, Fiona, Shapely, and etc. With groups of companies and institutions that are trying to figure out common standards and stuff like that. So we try to engage with the community as much as we can. In general, doing stuff in space is not easy, and debugging a satellite that you see like 10 minutes every 1 hour and a half is not easy as well. So yeah, you can imagine. So we're like facing all kind of different trouble, but we apply like we try to have an agile mentality as much as we can. And we have lots of projects that I could not mention in this talk because I wanted to be brief. So just ask around. And that's it. So if you have any questions, this is our greenhouse board. So you can see our open positions, our GitHub, because we have some open source there. I already gave a talk on some of these projects last year in Python Barcelona, and mail address if you want to contact us. So that's it. Thank you very much. Do we have time for...
We can do 1 or 2 questions and then we have Holden's talk.
Okay.
Any question? Please raise your hand.
So, actually, I was wondering if you test the plans in any manner before actually uploading them into the satellites to make sure that everything will actually work.
That's a very good question. We have an engineering model in the factory in Uruguay that it's a satellite very much like the others, but it's standing in the ground. And we can test lots of stuff there, but there's one specific thing we cannot test, which is the maneuvering stuff, because like the satellite needs the GPS data and the magnetic field of the Earth and then information from the sun sensor and from the star trackers. So there's like a bunch of information that the satellite is using to know where it is and where it is pointing to. And basically we have to fake all of it in some very nasty way. So it kind of works, but it's not foolproof. So we're like trying to work on better ways of doing it, but it's something that we are currently struggling with.
Actually, like how much logic is there in the satellite itself? Because I thought that it would be more like, okay, so at this point in time, do this and then do this other thing. It would be something more like a set of instructions.
The thing is that if we plan to have like 200 satellites, we want to plan them as in the simplest way as possible. So we try to put as less logic as we can in orbit, because we can control on the ground while we're planning what's going to happen, because it's easier to predict and easier to debug and everything. So there's some logic on board, but it's very little things. So the satellite knows if you tell it, okay, do this maneuver, then it knows how to do it. If you say switch on the camera, take a picture, it knows how to do it. But it's not like, okay, so the camera didn't switch on, now what do I do? No, we have to program all of that in the set of instructions. So it's more declarative.
How easy it is to change cell phone satellite once it's in orbit?
Well, change the operating system. No. Change the Python version. No. And depends on what you want to change. We have like a process of release that is very much like the release process that you probably have in your company. So we have like a continuous integration process where you tag a release, then it goes through all the testing, and then it has a deployment, and then it goes directly to the application that uploads that to the satellite, and most of the stuff is automatic. So like we have a way to do releases and to coordinate between releases of different projects. But to change fundamental things of the satellite, it's not that it's difficult, but it takes a lot of time to upload, so it's not worth it most of the times.
Why do you use GNU radio? Where do you send the data? Are you sending data directly to the satellite or not?
Yes, we have a network of ground stations, not only in Kiruna, but we also have stations in the Antarctica, and in Argentina, in Italy, and in South Africa, and we're planning to open some more. And I don't know that much about the radio part because I'm not a radio amateur myself.
I think it should be in C++ or C.
Yeah, exactly. So that part is, we wrap it in, I don't know if it's C or C++. Okay, so thank you very much.